In the early darkness, before galaxies formed, the young universe was a quiet space filled with hydrogen and helium waiting to come alive. This time, called the cosmic dawn, holds a mystery that puzzles astronomers. How did giant black holes, billions of times the sun's mass, form when the universe was only 1 billion years old? Traditional theories suggested slow growth through mergers and accretion, but these massive black holes seem to appear fully formed, defying explanation and requiring new ideas. Into this enigma stepped astrophysicist Jonathan Tan and his Pop-the-One theory, proposing that the universe's first starlight didn't flicker timidly into existence, but detonated in a blaze of glory orchestrated by dark matter itself. Picture the infant universe, still shrouded in its primordial darkness. Gravity had only just begun tugging together pockets of pure hydrogen and helium, the simplest elements, forged in the Big Bang's fading afterglow. In ordinary circumstances, these clouds would slowly collapse, heat up, and ignite into stars, much like the process we understand today. But according to astrophysicist Jonathan Tan's provocative theory, something far stranger and far more explosive was at play. The culprit? Dark matter. Unlike the normal matter that makes up stars, planets, and people, dark matter doesn't shine, reflect, or interact with light. It reveals its presence only through gravity, tugging invisibly on galaxies and shaping the large-scale web of the cosmos. Yet in Tan's Pop-the-One scenario, dark matter was more than a silent bystander. It was the hidden fuel sparking the very first cosmic fireworks. Here's how it worked. Within those early, dense clouds of pristine gas, dark matter particles, if they were the self-annihilating kind, many physicists suspect, didn't just sit idly by. When they collided, they annihilated one another, releasing colossal amounts of energy in the process. Imagine tiny, invisible sparks detonating deep inside those collapsing gas clouds, supercharging their cores far beyond what gravity alone could achieve. Instead of waiting for nuclear fusion to slowly take hold, these proto-stars were essentially turbo-ignited by dark matter itself. The result was nothing like the stars we see today. Modern stars are metallic in astronomical terms. They contain heavier elements like carbon, oxygen, and iron that regulate how energy flows through them. Those elements act like thermostats, keeping stars stable and relatively modest in size. But the first stars, unpolluted by any previous generations, had no such stabilizers. Fueled by dark matter annihilation, they ballooned into true cosmic leviathans, supermassive giants that could reach hundreds of thousands of solar masses. To put that in perspective, our sun looks like a candle next to a bonfire. Inside these monstrous objects, conditions defied imagination. Their cores roared at temperatures topping 1 billion degrees, hot enough to forge, in mere moments, the heavier elements that take billions of years to accumulate in today's stellar furnaces. These stars weren't just lighting up the cosmos, they were churning out the raw ingredients for planets, life, and everything that followed. But such brilliance comes with a price. Radiation pressure from their blazing interiors pushed violently against their outer layers, threatening to rip them apart. Stellar winds howled outward at thousands of kilometers per second, tearing chunks of gas into interstellar space. With each breath, these giants seeded their surroundings with the universe's first dusting of heavy elements, scattering the building blocks of chemistry across the cosmic void. In just a few million years, a blink in cosmic time, these dark, matter-fueled titans burned through their lives. They were too unstable, too massive to last. But during their short reign, they left an indelible mark, rewriting the rules of star formation and laying the groundwork for everything that came after. They were crucibles in the truest sense, forging light, matter, and possibility from the darkness, with dark matter itself as the hidden hand stirring the fire. If the birth of the first dark matter-fueled stars was extraordinary, their death was nothing short of cosmic theater. Imagine a universe still wrapped in twilight, silent, opaque, and filled with an endless fog of neutral hydrogen atoms. Light, though present, could not travel freely. It was constantly absorbed, scattered, and muffled by this atomic haze. The universe was a dark ocean, waiting for something powerful enough to lift the curtain. That something was about to arrive. As these supermassive populations of stars reached their breaking point, they unleashed energy on a scale the cosmos had never witnessed before. For most of cosmic history, stars and galaxies reionized hydrogen gradually, like a dimmer switch slowly turning up the lights. But according to Jonathan Tarn's daring model, the first giants didn't wait politely. They detonated. Their ultraviolet radiation erupted outward in waves so fierce that they tore electrons away from hydrogen atoms across vast intergalactic distances. This process, ionization, transformed the universe almost overnight. Instead of a slow dawn, Tan imagined a single blinding flash ionization, like the universe suddenly flicking on a trillion floodlights. In that instant, the fog cleared. Space became transparent for the first time, allowing light to travel freely across billions of light years. The cosmos had gone from opaque to crystalline in what amounted to a cosmic heartbeat. Picture it, a sky not studded with points of light, but flooded in every direction by the brilliance of a trillion suns exploding at once. This was not the gentle sunrise of ordinary starlight. It was a flashbulb moment on a galactic scale, a lightning strike that illuminated the entire observable universe. The energy involved was staggering. These ultraviolet tsunamis carried enough power not only to ionize hydrogen, but also to reshape the very dynamics of the young cosmos. Some astrophysicists speculate that the sudden injection of energy may have nudged the expansion rate of the universe itself, potentially offering a clue to one of modern astronomy's most stubborn puzzles, the Hubble tension. That's the nagging discrepancy between how fast the universe appears to be expanding when measured by nearby galaxies versus when measured by the cosmic microwave background. If Tan is right, this flash ionization event could have literally changed the tempo of cosmic expansion. But the drama didn't end with the physics. This light show also set the stage for everything that followed. By ripping electrons free, these stellar behemoths altered how gas cooled and condensed, influencing how the first galaxies assembled. The ultraviolet flood created new chemical pathways, cleared out star-forming regions, and accelerated the evolution of cosmic structure. In many ways, this brief but furious event wrote the opening chapter of galactic history. And then just as suddenly as it began, it was over. Within only a few million years, these titanic stars collapsed, their flash fading into silence. Yet their legacy endured. The universe was no longer dark. It had been shocked into transparency, its fog lifted, its stage illuminated. The cosmic dawn had not been a gentle rising sun, but a supernova-scale fireworks display, an inferno so bright it left an imprint we can still detect in the afterglow of the cosmos. Every story of fire eventually ends in ashes, and the lives of the first superstars were no exception. These population 3-1 giants, swollen to hundreds of thousands of solar masses and blazing with the fuel of both fusion and dark matter annihilation, lived fast and died young. Unlike today's stars, which can linger for billions of years, these titans burned through their existence in just a few million, a cosmic blink. And when the end came, it wasn't a quiet fade, but a collapse of almost unimaginable violence. Their cores, bloated by mass and stripped of stabilizing elements, reached the ultimate point of instability. For smaller stars, the finale might be a spectacular supernova, scattering iron and calcium across space and leaving behind a dense neutron star. But for these colossal objects, no such intermediate stage was possible. Their sheer weight doomed them to a more dramatic fate: direct collapse into black holes. In an instant, entire stars, thousands of times the mass of the Sun, imploded under their own gravity. The result was the birth of black hole seeds, so massive that they dwarfed anything the modern universe can produce. While today's stellar black holes typically form with a few solar masses, these primordial seeds could weigh up to 10,000 suns. It was as if the cosmos had skipped steps, creating monsters fully grown. And these black holes were hungry. Freed from the dense stellar material that had birthed them, they began to gorge on the surrounding gas left behind by the flash ionization. In theory, physics imposes a ceiling on how fast black holes can grow, the so-called Eddington limit, where radiation pressure from infalling material pushes back against further feeding. But these ancient beasts ignored such limits. The low metallicity environment of the young universe, coupled with abundant cold gas streams, allowed them to devour matter at rates 40 times higher than the Eddington threshold. They were, in effect, cosmic gluttons with no restraint. As these black holes grew, they transformed into gravitational anchors. Around them, galaxies began to form, their swirling gas and newborn stars drawn irresistibly into orbit. Some of these galaxies merged, funneling even more material into the maws of the central black holes, accelerating their growth further. In only a few 100 million years, these seeds had become the supermassive black holes we now glimpse with the James Webb Space Telescope gravitational leviathans, weighing billions of solar masses when the universe was scarcely a billion years old. The implications are staggering. Our own Milky Way's central giant, Sagittarius A 4 million solar mass black hole, lurking 26,000 light-years away, may well trace its ancestry back to one of these primordial titans. If true, it means that the very heart of our galaxy is a fossil, a survivor of the universe's first great age of fire and collapse. In their deaths, these first stars reshaped the cosmos. They left behind not only the black holes that would dominate galactic centers, but also the heavy elements scattered by their furious winds. Every planet, every life form, every atom of iron in our blood carries the fingerprints of that era. The universe's first light show ended in darkness, but from those gravitational graves, the scaffolding of cosmic structure was born. Today, 13.8 billion years later, the evidence for this fireworks show lingers in the polarized whispers of the cosmic microwave background and the unexpected maturity of ancient galaxies observed by JWST 914. Yet the theory remains contentious. Some astrophysicists champion alternative models like primordial black holes or super Eddington accretion 811. Confirmation may come from next-generation telescopes probing the universe's dark age for spectral imprints of population 3, stars, or their ionization signatures. If verified, Tan's vision reshapes our origin story. Not a stately awakening of stars, but a single, violent dawn where dark matter sculpted the first light and dying giants birthed the gravitational anchors of all cosmic structure. Anyways, folks, that is all for this video. If you enjoyed the content, be sure to leave a like and subscribe to see more interesting videos like this.